Okay lah. So we go.
Okay, so it's 2:59, but if you are comfortable enough to start now, you can start now.
Okay. Good morning, distinguished guests and lecturers. I'm Ryan, and I'll be presenting on my final year project about Internet of Things standalone photovoltaic monitoring system. And these are my supervisors and TSO that has helped me throughout this project. And the table of content that I'll be going through today will involve the purpose of project, the hardware system overview, the software system overview, and also the conclusion. So what is the purpose of the project, we are wondering? So it is to actually collect data to be a standalone system, and also to test different panels to make sure we know which panel has the best efficiency for us to improve our solar electricity generation. And one thing that I put down, which is important to me, I feel, it is to play a part in Singapore's sustainable development. And now we will talk about the software that I've used throughout this FYP journey. Firstly, I've used AutoCAD to draw schematic drawings of electrical designs, which is very helpful for any electrical engineer of any scope to understand what is the system about, so that we can actually troubleshoot or even change the wires or the MCBs accordingly if there's a fault. And also Ultimaker that's used for 3D printing. So we actually wanted to try to save costs by 3D printing our own mounting device. So we actually picked up skills from Ultimaker to 3D print our object. But what I've realized about Ultimaker, using the PLA material, it is actually not PV resistant. So what does this mean? Under the hot sun, the material will actually degrade. That means that we need to find another solution. That's why I've experienced Creo and Adobe Illustrator. So what's the difference between these two? Adobe Illustrator together with Creo 4 actually lasers cut the mounting device, so it is heat resistant and PV resistant. And also, not forgetting LabVIEW 2020, which is a product of National Instruments that I'm heavily using in this particular project. And not only that, I have also explored GWeb development, which is also a product of National Instruments. And now we will go through the current hardware overview. So this is my current setup. On your left, we have the housing unit that holds the data logger, the MPPT, 2 batteries connected in parallel to increase the battery capacity, and also a irradiance sensor at the top, and also a solar panel together with a transmitter. So let's go through what are the wires. So the communication protocol used in this would be Modbus protocol, RTU. So the sensors will be connected to the logger, also known as the Raspberry Pi, to retrieve data and also to transmit data to the cloud service. So how is it transmitting to the cloud service, you guys might ask? It's actually through an Ethernet cable to the transmitter client. So as you can see from here, there's a client and a host. So the client is actually communicating with the host. Together with that, we have a 4G router that's also connected to the host that provides the internet access. In this case, will be 4G cellular. With internet access, the data will be able to transmit to the cloud service for it to be retrieved by any user interface from anywhere in the world. All we need is just internet access. And now this is an example of the scaled out system. So as you can see, the difference in color of the system panel. So in fact, we are actually trying to test out the difference in solar panel. So theoretically speaking, this system can hold up to 254 devices with one host and a few clients. The reason being, because we know it's TCP/IP, the IP address only accounts up to 254. So we can load up to 254 systems. But at the same time, we must take into the consideration of the bandwidth. If the bandwidth is not good, we won't be retrieving the data we want, and there might be problem afterwards. So my solution to that is to either add more routers or just keep the monitoring system modular at from places to places. And also we can retrieve the data from anywhere of the world with internet connection. And now we'll be talking about the software system overview. So these are the few modules that I've created and made into a sub-VI, a more compact version to make sure the code is tidier, which will be embedded into the Raspberry Pi to make sure that all the data is collect, receive, and also log the potential error so that I can troubleshoot the problems later on when I were to do an update on the system. So this is the flowchart of the backend code that is embedded into the Raspberry Pi. So essentially, this is what is happening once the Raspberry Pi is turned on. And this is the block diagram of the program. As you can see, it is very neat, as you know that each loop serves its own purpose. So one particular loop just focuses on the data logging, one particular loop just focuses on the error logging, and another one for the transmission and also data acquisition. Also, I understand that hardware devices might actually come loose if you don't touch it often. So I've actually implemented an establishing reinitializing process in the loops, so that in any instant where the device is a bit loose, it will actually try to reconfigure itself to make sure that the system still continue running and not just be dead outside in the standalone. If not, an engineer will need to go to the system and make sure everything is connected smoothly. And now this is the back-end front panel. So from the front panel, it is actually where we will input the important information that we will need. So we can divide it into 4 sections. One is for the error log, one is for the data transmission, one is for the data acquisition, and one is for the data logging. So for the data acquisition, we will need to know what data we want to retrieve. With that being said, we must know the starting address and the number of inputs you want. So it is all actually set over here at the serial config circle at your extreme left. And at the top, we can see 2 file directions, 2 file path directory, and also a URL string. So the URL string is actually the cloud service URL, which is where the data will be transmitted to. And the 2 file logging path will be the file directory inside the Raspberry Pi. And this is where the data and the error will be logged respectively. And at the side, we can see DAQ error display, data logging display. So all these error messages is what I use to check my software to make sure everything is running before I deploy it in real time. And now I would like to bring you guys through the user interface. And this will be the user interface VI. Once I were to open the user interface later at the back for demo, this is what we will observe from the user interface. And now the user interface block diagram. As you can see, there is one event structure loop that is allocated for user inputs, like a click from the user, a scroll from the user, and button inputs. And we have 2 loops, one loop for retrieving the data, and one loop to process the data and to display the data on a graph. And now, the user interface front panel. I've designed 7 tabs for us to explore later, if we have time. So we have the home, the analysis, the solar panel, the battery, together with the temperature and the irradiance. So I've actually compiled past data so that we can actually see the relationship of how the weather condition actually affects the whole system. And some highlights I would like to mention in the whole project will be GWeb development, analysis of data, and experience. So starting off with GWeb development. So GWeb development is something unlike our usual LabVIEW, because if we were to use LabVIEW, we will need to host our user interface with the app. So if we didn't download the application, we wouldn't be able to use the user interface. But with GWeb development, we can actually upload the UI onto the web application, and with the correct URL, anyone can just access the UI, which makes it so much more convenient for anyone that wants to view data. And also analysis of data. So what's the point of collecting so much data if you don't analyze it, right? So I did a few calculations my own to calculate what is the remaining time left for the system that it can run on without charging. So this is an example, 20 hours and 45 minutes. So ideally, with 100% capacity, the system can stay up running for 2.5 days. And also the experience that I did my testing on NUS Rooftop, which I'm very honored. Thank you everybody. And also, now I would like to go through the Internet of Things overview. So the remote standalone monitoring system provides convenience. As you all know, standalone system would not need a connection to the power source. So if you don't need to connect the system to a power source, ideally it can be at anywhere we want it to be. All we need to do is just to have a testing site. Not only that, the software application used is industry graded. So as you all know, our working partner NUS series is also using LabVIEW, which shows that this software is actually used by big industry leaders. And also I've collected and transmitted data and retrieved it accordingly, and together analyzing data to make use of the data to make sure that we don't waste the data collected. And also the data, as we see just now, it can be retrieved from multiple systems. So with multiple systems, we can actually test multiple panels at once, so that we do not waste time and wait to test 2 panels at one time. And with that, I would like to conclude my presentation. The objective of the FYP is met beyond its initial proposed solution. Not only that, I understand the importance of solar PV monitoring system, and also electrical engineering does have a role to play in the sustainable development. Not only that, it provided an amazing opportunity for me to display and showcase what I've learned in school. And with that, I would like to thank everyone for this presentation, and we would move on to Q&A.
Okay, thank you, Ryan. You have 10 more minutes. You can actually do the demo for 10 minutes before the last 10-minute Q&A.
Oh, sure.
Okay.